Hello, hello. I think you hear me right. You should check your audio if you cannot hear me. Okay, let's begin. So, today we will go through data representation in C program, integer, character. I think most of you already hear it. We will also dive into the binary word. Have you seen our CS teacher shows a tree made by 0 and 1? That's binary and that's so important in computer world. Here's a question for you. And after this class, you should get the answer to these questions. First, why we need data type in C program. So what's explicit cast and implicit cast, which are more dangerous? How to expand bit representation from short integer to integer in C program, and which probability of integer algebra does Boolean algebra break? So you will get the answer if you if you focus on this class. Okay, so reminder, let's lab tomorrow, and our TA, our fantastic TAs, will help you with your project 01. Also tomorrow, project 02, the bits and bytes will be released tomorrow. For project 01, the due date is on Monday, 11 p.m. So don't forget to submit to Graphscope uh, of your project. And last day to add the job is also this Monday, so be careful. Okay, so here's the example. So um, Aaron 5 is brought because they did not took this class. They are bad student. They did not take this fantastic class, so they made some trouble. Their algorithm is working for Arians 4, but it's called overflow for Arians 5. Um, why? Why they do it? We will answer this question in the end of our class. So, why do we care so much about bits and how to manipulate it then? So, we know bits are very important for low-level systems programming tasks. In C-type, the C-type has a specific number of bits that can be used for low-level data structure known as bit fields. Bit fields are important for low-level tasks such as representing sets in compiler analysis, direct accessing system resource, processing, reading and writing in terms of string of bits, such as processing package in network programming. And we can see it's so important in our computer world. Okay, so can you tell me what's the number 1011 means here? Any answer? Okay, I cannot hear any answer because this is a video. Actually, 1011 could be 11 if it's an on-site integer, but it also can be -5 if it's a signed integer. Also for the number 01, 0, 0, 0, 0, 0, 0, 1, it also have different meaning in different case. It could be a character, A. It also can be an integer, 65. So how we know this number means? So we need data type. We define variable type first to avoid this kind of ambiguity. Okay, so here's the example. So each machine has a word size. Some machines are 32 bits. It's like 4 bytes. But in this kind of machine, they have limited address. It's only up to 4 gigabytes. So you must have same idea as mine. That's so small. I need at least 8 GB to play my video games. Yes, because this is so small. So new system are 64 bits. It's 8 bytes now. Potentially, address has like 1.8 times 10 power of 19 bytes. But no matter the word size is 32 bits or 64 bits, machines support multiple data format. Each format could be fraction or multiples of word size, and it's always integral number of bytes. So in here you can see for side number and unsigned number, the bits means different things. So we need type. So as I said before, you cannot decide what the sequence of 0 and 1 means until you figure out the type. It could be signed or unsigned integer. It could be floating pointer. It could be part of string. Could even be a machine instruction. So we need machine to interpret what those bits means. That's why we need type. The type can give a machine a hint how to interpret these bits. Okay, so here's this example. The include in C programming is include a library, the standard library or the library you create by yourself, and uh, there's a in main function there's a string literal uh, main main function return integer, and there's no argument. So actually, this function is very simple program, just like a hello world program. Let's see how we do it. Okay, so now we compile it, this code, and we execute. Okay, so you can see when we execute this, it say uh, the program is found. So here's another example. This example shows uh, different data representation in C program. So what about if C is character 0, is the same as integer 0, and in this case you can see the variable C is 69, and we try to print f of len in different type. Percentage C means character, and percentage D means integer. And let's see the example. Okay, you can see the example shows it's different. The uh, the 69 could be character E. Also, uh, it could be a number. So yeah. So here's another example. This example shows the sizes of different type in C program. And be careful, this is an example from 32-bit version. So don't just mess up. It try to give us the clue like how many size of integer, how many size of uh, short integer, unsigned integer character, and yeah, the result shows there's different. Character is 1 byte and integer is 4 bytes. Short integer is 2 bytes. Okay, so integer is very common. It's a common type in programming language. It reflects the natural size of integers on machine. In first IBM is very old version PC. It's only 2 bytes, but in current PC, even 64 bits PC, it's like just like 4 bytes. It's 32 bits. But be careful because we don't know, maybe newer machine or something they change it. Here is a table of the sizes of each type in different machine. And you can see, as I say, the integer tag 4 bytes in different 32-bit machine and 64-bit machine. But be careful that long and pointer are different on different machine. Okay, so we know pointer is used to saving address of a variable. So for 64-bit machine, it should have a size like a byte. Otherwise, it must cost like it don't have so many um, bits to save the address like uh, a a gigabytes memory. So we must have 8 bytes for this pointer to save address. So we have different type. Can we cast one to the other? So here, actually we can convert signed number to unsigned number. If you remember the last lecture, you will know a negative number is actually a very big positive number in unsigned integer. So after casting, non-negative value will keep same, but negative value will be turned into a large positive values. Okay, so implicit type casting is performed by the compiler on its own when it encounters a mixed data type in expression in the program. It's also known as automatically conversion as it's done by compiler without programmer's assistance. And implicit casting doesn't require a casting operator. And here, implicit type casting also occurs when we miss the type casting operator. So be careful because sometimes you think you just assign some value from other variable, but actually, if you did not check the type, it's due the implicit type casting, and it could change the value. Remember, if on side a side integer, a side number, if it's a negative number, it can be changed to a very large unsigned number. So watch out. This picture shows a casting example. If integer has to represent in 5 bits, actually it's not. Integer is represent in 4 bytes in current machine, but in this example we only shows 5-bit case. The maximum unsigned number is 31 and minimum is 0 for unsigned integer. But for signed number, the maximum is 15, which is 0, 1, 1, 1 in binary, and the minimum is negative number is minus 16, which is 1, 0, 0, 0 in binary. So the 1, 1, 1, 1 here is not the minimum value for negative value. Is actually just the minus 1. So after casting, minus 1 will be changed into a very big number. 31 is the maximum number in unsigned integer. So you can see that even you got a number is not a minimum in negative number, it can be changed to the maximum number, maximum unsigned number. So be careful when you do the casting. Okay, so here's the same pictures to support the same idea, and think about this. You can see the 0, 1, 0, 0, 0 and 0, 1, 1, 1, all this kind of stuff. And -1 is still 1, 1, 1, which is 15 in unsigned integer. Okay, in previous slides, we talked about the casting between two types with same size. What happens if we casting from a small integer type to a larger integer type? The answer is C will automatically perform sign or zero extension. This is an example. Xx is a negative number, and when we casting it to large size type integer x, we will see x is still the same negative number minus 1, 2, 3, 4, 5, since C automatically extend all higher order bits as 1. Yeah, can you see that? The xx to x. In x, the binary representation, you can see all higher order bits is 1. So it keep the same value. When then we casting another case is we casting xx to unsigned short integer and get the unsigned short integer 53191. Now we tested this variable to larger size to integer, and we can still get 53191. Why? Because it's do a zero extension in on this binary representation. It's extend the high order bits, all high order bits as 0. So we know for bit extension, C is a great tool, and we don't need to worry much about the value change. Here is how to do extension. When doing sign extension, it's just make k copies of sign bits. If it's unsigned integer, this method will copy k zeros for 0 or positive number and copy. Oh, sorry. So for when doing signed integer, this method will copy k zeros for 0 or positive number and copy k ones for negative number. This is sign extension. Okay, so for maybe we should get rest, maybe 1 minute for you to review this video. Then move to the expansion. Okay, so I think 1 minute is here. Did you get rest? If no, you can just like pause the video and then to get some rest. Okay, so let's continue. So for expanding, we know we can use 0 or sign extension. How about the truncating? For example, in 32-bit machine, if we want to casting integer, which is 32 bits, to short integer 16 bits, we need to cut it. We will drop off 16 bits, right? So this can alter its value, right? And if so, we can say it's an overflow because the value is totally different. But it makes sense because you drop off some information in a number. So that's totally make sense. So how we do this cutting? For unsigned value, we just mod it by 2 power of k. So it's like just mod. But for side value, we also do mod, but we do a unsigned to side value after to change it. So here we know for expanding, it's okay because the C will do a good job for us. It will extend 0 for positive number, and it's assign 1 to negative number. If it's assigned integer assigned number, but for the truncating, it's not. The number will lose some information and the value will change. It's cause overflow. So be careful on this. Okay, so this is a table shows the expression evaluation on different operator and operand type. So you can see the 0 equal to 0u means unsigned 0. -1 less than 0 is sign number. But -1 larger than unsigned 0 because the -1 in unsigned integer which equal to very big value. So in this case, the T max value is like 2 billion. It's a very big value. So or it's just 4 billion. Actually, it's depends on what's the size, but it's a very big value. So so in here you can see there's a point here. The key point here is that if there exceed an unsigned value and a signed value both exist in a single expression, it will implicitly cast the side 1 into outside 1. So just as I mentioned before, the implicitly casting is very dangerous if you did not aware of it. You can see if you set -1 less than 0, but it's a side number, it's okay, but it's unsigned number, yeah, it's boom. -1 should not larger than 0, right? So like like the first row, if the 0 is signed integer and 0u is unsigned integer, 0u means unsigned 0. It will change the signed 0 to unsigned 0, so they are equal. Another example is like 5, the row 5. Even 2, 1, 4, 7, 4, 8, 3, 6, 4, 7. This big number is unsigned 0, but compared to a signed, it's an unsigned number. Compared to a signed number, it's negative number. This signed number will be changed to unsigned number. Will be just like the 2, 1, 4, 7, 4, 8, 3, 6, 4, 7, no 4a. Yeah, it's a little bit large than this big number. So because it's implicitly cast to an unsigned number. Okay, here's the question: how many bits does this human brain have? The answer is 4 bytes. Can you see that? It's a joke, but yeah, if you take this case, you can understand why it's a joke. Okay. Now I want to move to bit manipulations. If you want to get the rest, you can do it now because it's a new topic, but I will still continue my presentation. So Boolean algebra is developed by this George Boole. He was a mathematician and logician. He developed ways of expressing logical process using algebra symbols, like creating a bunch of mathematicals known as simple logic or Boolean algebra. His master thesis developing a method for using Boolean logic to represent circles. So circulars. So you can see the bits 0, 1 are so important. So have so correlation to the our computer. His 1948 papers on communication theory each helped to define a field and revolutionized the way in which we view our world. So it gives us a computer world with the explanation of his major work in switching, genetics, information theory, and cryptography. Okay, so this is so just history. So what's the important? The important is the binary word is just like the computer word is just binary word, and that's a lot of zero and a lot of one, and now we need some operators to help us to like deal with this 0 and 1. So in here, I show you some operator we will cover in the slides later. The first one, and you must be familiar with this one, and or, and also exclusive or, and complement. Uh, that's two important one. Shift left, shift right. Actually, shift. Shift is important idea in this bit manipulation. Okay, here's the table for Boolean algebra. We say 1 is true and 0 is false. In your exams or assignment, if you forget or you think the operation is not so clear, you are not sure, try to plot this table for help. So here you can see the complement. It means if it's 0, it will be 1. If it's 1, it will be 0. And this operator is like if both 1 is give 1, otherwise it's give 0. The or is a little bit different. The or is if it's has 1 in either either variable, either operand, you will get 1. But both 0 can give you 0. And exclusive or means if if two numbers are same, you give 0. Otherwise, they are different, you give 1. So this is the operator in binary word. So okay, so here's another some example like Boolean, like if we say 1010, we do complement is 0101. Okay, so what's the idea here? Boolean operations are applied byte-wise on the bit sequence. So here you can see the just as I say, the first 1010 is changed to 0101, and if 0110 and 0010 will give you 0010, since only third bit in both sequence is 1. So this example, the first bit, the leftmost bit, that's 0 in the first sequence, so it gets 0. And you compare the second one, 1 and 0, it should be 0. And the third one, 1, 1 will give you 1, and the fourth one, 0, 0 will give you 0. And for all operation, you can see different things like only the last digits, both for both number is 0, so you get 0. Otherwise, you get 1. Okay, so Boolean algebra obeys some of the properties of integer algebra. So in Boolean algebra, we said OR means sum, and AND operator means product, and 0 is identity of sum, and 1 is identity of product. So here you can see that for Boolean for Boolean algebra, sum and product identity is not broken, because you do A or 0 means A sum 0 still equal to A, and in integer world, A plus 0 equal to A. For AND, A product, A times 1, AND means product, so A times 1 equals to A, and they are same thing. And another one is you can see the Boolean algebra obeys the 0 is product annihilator. So A times 0 must equal to 0. Then we say AND is product. So A times 0 is 0. Same thing. And another property it did not break is cancelling of negation. So complement of A is still A. Sorry. Okay, but there are two properties it break. First, the law of complement. In integer, the sum of 1 and minus 1 is 0. But in Boolean algebra, A or A's complement, remember OR means sum. So A or A's complement will give true, which equal to 1 is not 0. It also break the rule like every element has an additive inverse. It's break because you cannot see you cannot get a complement of of the value the variable, so make them do sum to get 0. So you cannot find any other complement, any active inverse of this component in binary world. Okay, so now we move to shift part. This is very important concept in computer science because you can easily do a product or division without using a complicated operator. You will understand this is very useful operator when you take more system course in the future. So let's begin. So first, I want you to think about 10 base integer. if we do one shift, left shift on integer 230, what it will be? Okay, if just like 230 we shift left, it will be 2300, right? Okay, so how about we do like 3 left shift? What it will be? It will be 230,000, right? Okay, so that's the idea. So when we do one left shift, it's just like we times 10 to this number. And we do 3 left, it's just like we put 30. We times 1000 in the we put 30 in the end of the number. Okay, so let's change back to binary word. Because it's binary, so when we do left shift, it's equal to we times 2 because it's binary, not 10. Be careful in this number. So we shift one number means we do a left shift means we times 2. So here's the process. When we shift, so first we draw away the extra bit on the left. Actually, we have to draw away because we don't have extra space for this number. This number, right? Because yeah, it's the space is just like a here. We cannot save 10 value 10 number in the space. So if we do 2 left shift, we draw away 2 bits on the left. In this example, we draw away the first one and the second bit is 0. We draw away 1 0 in this number. Then we put 2 0 in the end of this number. Okay, so if we shift x k times, it's equivalent to x times 2 power of k. So how about right shift? Same idea. If we do one right shift on 230, it will be 23, equal to like we divide 230 by 10, right? In a decimal word, but in binary word, it's different. So if we do a right shift on a binary number, means we divided the number by 2 for each right shift. So we do 3 right shift is divided by 2 power of 3 means it's divided by 8. So here's a question. What if we divide a negative number? Think about it. Okay, so here we have two kind shifts for different type. If it's on-side integer, we do logical shift. Just put 0 on the left after drawing out the extra bits in right side. We still need to drawing out the extra bit, just like we do left shift. If it's a side number, we do arithmetic shift. We put the most significant bit on the left side. For positive number, put 0. For negative number, put 1. Okay, then you must ask, if we draw away the bits on the left side, we must lose accuracy when we use shift to compute the division. Yes, you are right. But the number itself is an integer, so we won't keep number. We don't keep number after the decimal point, right? So which means when you do a shift, you might change a little bit the numbers, the value means, but you will get the similar number. So here's the example. When you do like shift, right shift on this number 10010001, when you do the 3 right shift on this one, you will get minus 14, not minus 13.875. So that's the idea. You will get the very close value. Okay, so here's a comparison between Java and C. For C program, it's decide which shift. It's just automatically decide which shift, local shift or arithmetic shift, based on the type of operands. If it's side type, it's do if it's side, it's do arithmetic shift. If it's onside, it's just do a local shift. But in Java, there's a different operator for different shifts. So so in C program, you have to know what it will do for different type of your variable, your different type number. Okay, so here's a question. In this video, we don't use icon, but you still can answer it for practice. Okay, so give you 2 minutes. No, maybe 1 minute. 1 minute is enough. Is 1 minute right? Or too soon? If you have not figured out what's the answer, you can pause the video and unpause it until you figure out. The answer here is this one. Because we shift 1001, 0001, the significant bit is 1. So first we draw away the 01 on the left side, on the right side. Then we put the significant bit, which is 1, on the left side. So it gives us 1110, 0100. Okay, so do you remember this disaster we saw in the beginning of this class? So what's their problem? So now I want to show you. Okay, so this is the source code. This is their code. You can see they did check on the for the integer range in the first part of this program. They checks for integer range for vertical velocity of rocket, so it's very good. But you can also find there's a dangerous part here is they do very similar execution, but they did not check in the second part. They just run pn derive on this variable. They did not check. So that's so terrible because even it's this small piece of the source code can make this huge loss of this country, make the huge. It's a terrible news for people, right? So be careful in type, be careful in casting. That's what we want to tell you in this class. So this is solution to fix it. Actually, we just add another similar if else statement to check the second part. Then we can avoid the overflow. So you can see even it's very small piece of the source code just couple lines source code. It's really matter. Okay, so now sometimes you will encounter a situation where multiple smaller numbers are packed into a single large one. Some reason for this are to save space in memory. Even the memory is so cheap now in current world. For sometimes you might still need want to save some memory, or it's for to fit a quantity into a single register. Uh, I'm not sure you are familiar with register, but we will go through in our class like later. But register is very small, like very small memory uh, since it can your CPU can access the register is very fast, but it's so small. So sometimes you want to put more information in just one register. It can speed out your CPU because your CPU don't need to act memory as a cache. Okay, so also it could because some hardware was designed that way, and you have to talk to it. So hardware problem you cannot avoid because someone designed this kind of hardware. So you have to know. Uh, or another reason might be to save sending bits over a network or communicate a device. Like you want to save time. You want to speed up the networking communication. You want to speed up the translation transition on the device. Okay, so this leads to requirement to exact range of bits in a number and to update range of bits. Okay, so uh, here is here I want to give you an example. So first we have a serious number of bits. The bit is just 1 byte. Is from starting from 0 on the right. So 1 byte can show like bit 7, bit 6, bit 5, and so on. Suppose we want bit 2 to bit 4. We just want this. We don't want other bits. We just want bit 2 to bit 4. How do we do it? So first, we isolate the bit using a mask. I will go to this. I will tell you what's a mask later. Which means we and the number we want to end. We want to find a mask and use the mask to select the number, the bits in the number. So the mask will be like this. If we want the bit 2 to bit 4, we set 0 0 1 1 1 0 0 means we set 1 if you want this position. Otherwise you just put 0. Then you can shift okay, then you can do the add of this because only one and only the bit and 1 can get the the bit itself, otherwise it gives you 0. So you can do this, then you can get these bits. But there's a final step, step 2. You have to shift it because from here you will get some number like a big number that's still 20 in the right side. So you have to shift it um, to get rid of unwanted 0 bit on the right. So in this case, you will shift it by 2. Do the uh, right shift right shifted by 2. Okay, so here we made it more formal. So how we generate the mask number, the mask series of the bit number. So first we know L minus R plus 1 means the number of bits you want to save. For example, from bit 2 to bit 4, we want to save 4 minus 2 plus 1 equal to 3 bits, right? Bit 2, bit 3, bit 4, there's 3 bits. Then we can do the number shift on 1 and subtract it by 1 to generate number of ones, couple ones. In this case, we generate 3 ones on the left and 0 for all remaining bits. Oh, 3 ones on the right and 0 for all remaining bits. So what's the idea here? Which is if we want 3, just as I say, L minus R plus 1 is 3 bits, and we want 3 ones. The position of 3 ones is on the bit 2 to bit 4. Then first, how we generate these 3 1? We just shift the shift 1, the value 1, shift it in by this shift is 3 times. It will go to the bit 4, and we minus this value by 1. You can get 3 ones in the right side of the sequence number. I will show you example later. Okay, so for L equal to 4 and R equal to 2, because we want a bit 2 to bit 4, we have 1 left shift 3 minus 1, which means we can get 1 like this after 1 shift 3. We get 1 0 0 0. We put 3 0 because we do the left shift 3 left shift, and we subtract 1, subtract this number by 1, and we can get 0 0 0 0 1 1 1. So we create a sequence number contains 3 ones. This is for mask function, mask number. Okay, then we shift these numbers to shift the number by the R bits. So like the case is like this. We shift this number by the R. In this case, it's 2 to generate a mask number. So in this case, you will get the value like this. We shift 0 0 0 0 1 1 1 left by 2. Then we can get 0 0 1 1 1 0. That's the mask number we want, because only the bit 2 to bit 4 is 1. Otherwise, it's 0. Note that this method works only for on-site field, on-site number. So be careful. Please be careful. Okay, so this is the source code we built in C program. And you can see the mask function here. We do the left shift, we minus 1. Then we do left shift again to change the position, to align the mask the position of 1 to the correct to the target bit. And then we do the mask. We end the mask and our target number. Then we do the right shift 2 by 2 to get the value we want. Okay, so this is extracting a range of bits. But there's another simple way we can do to extract a range of bits. So first, we have sensing. We have a bit 7 to bit 0 here, and we want to we only want bit 2 to 4. So first, we can shift left, do a left shift. So like we shift 3 to get rid of the bit 7 to bit 5 because we don't care bit 7, bit 6, bit 5. We don't care it. So we do a left shift on 3. Then we can see this number. We can get 30 in the end. Okay. After that, we do shift right to get the desired bit. How many bit we want to shift? In this case, we shift 5. We do a right shift by 5 bits, so we can get this number. So this is the target. This is the result we want. Okay, so this is a simple way, and this method can support side or on-site field. So uh, this could be a better way to do the extraction a range of bits. Okay, so here's the process. So first we shift left by n minus l minus 1 bits, which means how many left shift you want. Then shift right by n minus l minus 1 plus r bits. So then do the right shift. It will run logical shift or for unsigned number and arithmetic shift for signed number. So it's support on both number, not only for unsigned number. And if you are review the previous slides, this shift, logical shift or arithmetic shift, all about the type in C program. So let's say again, the type is very important concept in C program, and you have to check. Otherwise, you might got some problem. You might make a rocket boom, something like that. You have to be careful on the type in C program. Okay, so n. Okay, so n. What's the n? M is the size of data type to extract from. So in our example, our number is only 8 bits, but when you use this method, if you want to use this method, you have to care. You have to be careful. What's this n be in your system, in your machine? So you have to check the size before you use it, because the size not always be A. It could be 16, it could be 32, even 64, even bigger in the future. So here, for L equal to 4 and R equal to 2, with N equal to A, in our example, we have X, 3 left shift on X, then do 5 right shift on it. Okay, so think about this. I will continue in few seconds. Okay, let's continue. is the last part of this class, this slide. So let's just do it. Okay, so now we are talking about the extracting. How about updating? If we want to update certain range of bits in a number by some bits from another number, how to do it? Okay, so mask. Yes, mask again. So that's two methods we talk about in the extracting, and I think we both agree that the second method is more simple. But the first method gives us a very useful idea, very important idea is that the mask. Um, okay, so if you in following slides you are not familiar with how we generate the mask, I would suggest just go back a couple slides before to make sure you understand how we generate the mask and why we need mask. Okay, so let's continue. So if we need mask for updating. So then we shift the new value. New value means the bit we want to store from the bit the number contain the bit we want to store from. So we want to shift the new value, which means we want to arrangement of the left bits, no right bits on the new value we want to put into the number we have. Okay, so we shift it by R. We shift it by R, then do mask on it to save the bits in new value we want. After that, we want to clean some bits, the bit we want to update. So we clean the original bits in the target number. In this case, we need a complement of mask to clean it. I will show you why we need this, why we need a complement of mask. Then after that, we can do OR operator to the target number and some bits on new value. We can do OR to just then we can update these numbers. Okay, so let's show you an example to you will get a better sense. So in C program, first you get mask number, then you shift mask by the R, the 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 small bit number. In our case, is 2, the bit 2. Then we end with the mask. After that, we also do some clean of our target number to make the position, make the bit we want to update clean, and we do the OR on these two value to generate the updating value. So here's the example. So first, sensing L equal to 4, I equal to 2, and now we have a new value 0, 0, 0, 1, 0, 1, 0, 1, and we want to put 1, 0, 1, the three right digits, 3 right bits in this new value. We want to put this value, these bits to the to our target value, and our target number is 0, 1, 1, 0, 1, 1, 0, 1. We want to change the 0, 1, 1 underscore 0, 1, 1 part. We want to replace it with 1, 0, 1 in new value. Okay, so here is example. So we have new value 0, 0, 0, 1, 0, 1, 0, 1, and we want to put the last 3 bits 101 in the new value into the bit 2 to bit 4 in target value, which is 011. Okay, clear? The question is clear. Okay, so we first generate the mask. So if you don't remember how to generate the mask, go back to a couple slides before. You will understand it. Then here the mask is like 000 11100, which means only the bit is 1 is interested in our case. For other 0 part, we don't care the bits in that part. Okay, so we do the shift the new value by r. R is 2, so we shift it. Then we do the AND to with the mask. Then we got this number, and you can see 101 now it shows in the bit 2 to bit 4. It's fantastic because you know it's in the right position, and we do the mask, so we get rid of the extra 1 in the bit 6. So you can see the number we have now is a perfect number because it has all 0 in other bits. In a bit we are not interested, and it has the information 101 in correct position, the bit 2, bit 3, and bit 4. Okay, so perfect. And now we want to clean. So the third step is cleaning the bit 2 to bit 4 in the target value, in the original number. In this case, is the 4, variable 4. Okay, so we clean. So why is clean this? Because if we do complement of a mask, which means all 0 in mask will be 1, all 1 in mask will be 0. So if we end it, means all 1 in mask, because the complement is 0, so it will clean the bits, clean the bits 2 to bits 4. And for other part, because the complement of a mask will in other bits, for other bits it will be 1. So everything end with 1 will be the thing A, and 1 will be A. So it will stay, the other bit will stay, they will not be changed. So in this case, we can clean the bit 2 to bit 4 and remain the other bits in the new variable. Okay, so you can see then the last step is just OR, and we can see the result is like this. You can see the result shows bit 2 to bit 4 are from new value 101, and the other bits still remain same in the variable 4. So it's like this. So only bit 2 to bit 4 is from the new value. It's so cool, right? Okay, so in this case, we introduce the bit representation, and we know for different type, the number has different meaning. So watch out the type in C program. When you write the C source code, be careful the casting, the type you use. So it's so important. We also cover Boolean algebra, including different operations, include OR, include AND, include complement, include shift, right shift, left shift, and we know left shift and right shift is so fantastic You can use len along with other operator to do many things like extraction or updating the replacement, updating of range of bits. That's so cool. And in the future, you will know the shift, and the shift will give you a more efficient way to do the product or division. Okay, so let's class, and sorry, it's a video class, and I cannot meet with you guys in a class because I am out for a conference, and wish to looking forward to see you in next week, and hope the new project you will like the new project, and if you have any question, remember go to the lab section, and if you have further question the TA cannot help you, just come to my office hour, and thank you for watching this video, and see you next week.